Hello and welcome to another day of Advent of Code. We're back for day 19, which, oh boy, day 19 is a doozy. But let's jump into it. Okay, and yeah, this one took a real long time. I spent, this is my longest day so far by a long shot. So this problem is fairly difficult. But let's jump into kind of the data setup and how I approach the problem. Okay, so the input of this problem is a bunch of scanners and it lists the 3D points that they detect. So here's a few lines of my input, for example. So you can see we find scanner 0, it has a bunch of points here. Then we see scanner 1. My text editor is highlighting this weird because it thinks that it's a diff for some reason. I guess it kind of looks like a diff, so maybe that makes sense. Right, but anyway, these scanners have a bunch of points, and the scanners may be in different orientations relative to the other scanners. And what I figured this out to mean is that their X, Y, and Z coordinates might be in different positions or in different signs. Let me show you a little diagram of kind of how I thought about this. We're just going to look in 2D space, but then you can imagine the same thing being applied in 3D space. So let's draw just an XY plane here. I'm not going to bother to label the axes because it actually doesn't matter in this case, and they could go in any sort of different direction. Let's consider a point that, according to some scanner, is right here. And let's call that, I don't know, 3, 1, for instance. Now, based on how the scanner is rotated, this could actually appear in three other positions. One that's down here, one that is over here, and one that is up here. And when you perform rotations, the way rotations work is you swap the coordinates and you mark one of them as negative. So if we go down here, you would swap the coordinates to 1, 3, and this is actually 1, negative 3. And then you would do the same coordinate swap and the same negative application. So this, you swap, you get negative 3, 1, 3, 1, and then you negative the y coordinate. That's how you do a clockwise rotation. And, accordingly, this is also going to be swap the coordinates. You have negative 1, negative 3, which just becomes negative 1, 3. So that's how those 4 coordinates show up. So that's one set of the coordinates. Where the bot would rotate, or the scanner would rotate, and it would potentially see these in different locations based on its canonical choice. The other option is that it flips. So say that it's looking up, or sorry, it doesn't matter which direction. Say that it's looking up, and then suddenly it starts, it actually is looking down. So these are actually mirrored. So then you have to consider each of these points as well. From each of these 3 mirrorings. And these are basically all of the points that it could see in this particular XY plane. But since we're working in 3 dimensions, we actually have 3 different planes to care about. And so you would actually have to project this across another axis and another axis. Of course, when it's, Z0, it's less interesting there. But because of this, you basically need to check all of the axes against all other axes and all other signs of axes, because the thing might be rotated in a different way. Okay, so that's this part. Adjacent scanners will overlap by at least 12 points. So some of the scanners are adjacent to some of the other scanners. In the input problem, the sample that we got, in the sample we got, I believe it was 0, 1, 1, 4, 4, 2, and 1, 3 were all adjacent to each other. And the input problem actually has a lot of really useful information for debugging your solution, so I would definitely check out the pros that Eric wrote up there. Right, and so in part 1, we have to find the total number of points. Now, I spent a lot of time thinking about how to solve this, and the solution that I came up with is to try and find these overlaps, but doing that by diffing all of the points in one scanner with all of the points in the other. And if we successfully find an adjacent one, we should find the distance between one of the axes always being the same number for at least 12 points. I guess not always being the same number, but being the same number for at least 12 of those points. But we need to compare every single point against every single other point in the two scanners to figure that out. And we may need to do some of these axis permutations to do that as well. So if we're just considering like the x-axis from scanner 1, we need to consider the x, the y, and the z-axis for scanner. Sorry, this is scanner 0. So if we're looking at the x-axis for scanner 0, we need to consider the x, the y, and the z-axis for scanner 1. We also need to consider both the positive and negative for all three of these. And so just to figure out the x-axis, we need to do 8 comparisons. Or no, 1, 2, 3, 6 comparisons. Yes, so we need to do six complete comparisons here. And if we ever find a situation where a lot of the differences line up, then we know that that is the correct axis to compare scanner 0's axis against scanner 1's axis. Scanner 0's x-axis against whatever axis is in scanner 1. Then you can do the same thing for the y-axis and the same thing for the z-axis, and then you can figure out which axis in this scanner maps to which axis in this scanner and what sign it is, and from that you can figure out what the position is. So I'm going to show you kind of how I walked through that and how I figured that out, because there's no way I'm running this code live again because it's a couple hundred lines. I guess it's like 110-ish lines. Okay, so let's start with kind of the easy stuff, just like the parsing. So this is how I parsed my scanner. I had a scanner ID. I technically didn't need this, but it made it convenient for debugging. I also had a list of all the points, and the way I pulled that out was getting the lines from the input, parsing the scanner ID out of the first line, and then sticking all the points into a list. Next, let's jump to our actual computation function. So this is where I split each scanner out. Again, this is a nice little trick that I've seen a lot in admin of code, where you split on double new line to get them into their each their own chunk. I had a mapping here that mapped the scanner ID to the scanner. I used this later to do a graph traversal. So basically what the high-level way that I approach this problem is I started with the scanner that we are going to assume is at 0, 0, 0. And then I tried to find all adjacent scanners to that, and then all adjacent scanners to those, and all adjacent scanners to those, et cetera, basically building out a graph. And so this actually looks very similar to the depth first search that I've done in a bunch of other problems, but in this case, we are doing it with a very hard to find edge. Cool. So from that, I also have I have this edge, this axis info class, which is going to represent how I map the particular axis to the other particular axis. So let's say we're looking at the x-axis. This might be either 0, 1, or 2 mapping to the other x, the other y, or the other z-axis. I figure out the sign here to figure out whether I'm looking at the negative or positive version of those three axes, and I record the difference between those. That way I can just kind of figure out how far away the points are after that. And that's what is stored inside of these x edges and y and z edges. So this is me trying to figure out the potential other scanners that line up on these three axes. And in my in the sample data, they end up always overlapping. I don't think that is necessarily true, but I made that assumption and simplified based on that. So let's take a look at this x-edges from function and how I was able to take the current scanner that we're looking at, as well as all of the other remaining scanners, and a little bit of remaining there, so I eliminate every scanner because I don't need to rescan the ones that I have already visited. So that's how I keep track of that here. Oh, this should say scanners by ID. Okay, there's a tiny bug here, but the code works fine without it. Oh, actually no, it's fine because I do it right here. I don't know why I did this here. This should just be scanners 0 dot points. Scanners by ID 0 dot points. Okay, it doesn't matter. It ends up being the same thing because these line up the same. Okay, but yes, let's look at this x edges from function. X edges from. So we take in the scanner and we take in all of the remaining scanners. And basically what I do is that same permutation that I was talking about earlier. I try each of the axes in the other points, and I try each of the signs, and I'm just trying to match the source's x-axis against whatever other x-axis here. And I'm basically just counting the number of differences here. And I know that if I find a very common difference that has more than 12 matching edges, then I have matched the x-axis of the source against whatever other axis in the other one, and I can record that down here. And so if we take our sample problem, and if I drop a breakpoint right after this, and we run this, as part 1, yeah, so we can see here that the zero thing only connects to 1. Of course, this is not super interesting. Let's find another one where there's more than one. I believe 1 connects to 2 of them. Yeah, so this is source.sid. Yeah, this is from 1. We know that on from 1 to 3, the x-axis connects with the other x-axis, but it is negative. And it connects with this other x-axis, or sorry, with 4 it connects with the y-axis, and it's negative. So that's kind of what this x-edges is. From the x-edges, I do basically the same approach to find the y and z edges. So that's what this is here. Though in this, I make the assumption that if we've matched one axis, then the other 2 axes are going to match as well. So I don't bother looping over every single destination ID. I just use the one that I matched from the x-axis, and basically do the same math here. Figure out the differences, store them in a counter, and if we get a large number, then we know we've matched those 3. So if we look at x edges and y edges and z edges, oh, actually, we have not computed the next ones yet. We need to go 2 lines down. Why don't those match? All right, so x edges, y edges, and z edges. You can see we have figured out the difference between each of those axes here. Now note these numbers are a little bit different, and we get to that in a second. These are actually the final answers for the positions of the bots, and the reason that I did that is mostly for sanity's sake. So once I figured out where these edges are, these numbers are relative to the position of the previous thing. And at the start, the previous thing is at 0, 0, 0. So it's very easy to know exactly where the thing is. But if you don't adjust all the positions of the points, you kind of lose track of where the bot is, and it just makes for a bunch of fiddly math. I had it mostly working, but this was way easier to reason about. The way I reason about it is I just shift all of the points in a scanner. Once we know where it is, we just shift it back to the 0, 0, 0 and the orientation that the first scanner has. That way you can kind of just think about all of these points after you've shifted them being at the origin. And so then if you were to compare the modified bot against another bot, its difference is just going to be the difference from 0, 0, 0, which is really, really, really convenient. So I just basically swapped all the points out with their adjusted positions. I also update my all points because we know these are now normalized to 0, 0, 0, so we can record them all in our all points. And now that we've jumped to this next scanner, we can recurse essentially. Of course, this is the non-recursive, this is the iterative depth first search, but if you were doing recursion, this would be where the recursion would happen. And that's basically it. So my algorithm comes down to is like find the common differences, figure out which edges match to which other edges and what signs, adjust the points, and then stick them into your all points. And so part 1 is just figure out what all the points are. Part 2, since we have recorded these scanner positions, which technically aren't needed for part 1, I could comment this out for part 1 and it would still work. Part 2 is to take all of the scanner positions and find the furthest apart ones. And that's just a very, save it. I don't remember what I changed, but we'll save it. That's basically the same algorithm we've seen a bunch of times, which is like take one point, compare it against every other point, and compute the maxed difference here. And we're using Manhattan distance, so it's just the absolute value difference of all of the points. But anyway, that's day 19, which, oh boy, day 19 was was a lot of work. But hopefully this made sense, and I will see you around for the next day.